Okay, I'm going to do a mic check with the other computer, so you may hear me talking in the background. All right, sounds like the mic is working. Okay, so let's deal with some of the changes I've talked about. I started thinking for those people who are attending, I want to be able to give credit to them. And since it wasn't part of the syllabus, it has to be extra credit. So let me describe that real quick. So during a lecture, in the audio stream portion of it, I'll be giving it just a simple word. And if you go over to the course site, you'll see something like this. Okay, so let me get right down here. Okay, first of all, let's see. I've kind of played with this. So first of all, if you are logged in a Google browser and you sync your account, it will show this little box. If you are not and you're using another browser, this box won't have your Gmail name, but it'll have another different box there. So that you don't have to enter anything in. This, you enter in your tech email. I'll show you the back end of all this in a second. And then this, you enter the word of the day. Once the word of the day, of course, is mentioned in the audio stream of the lecture. So today, I'll just use the word apple. And let me show you what happens. Now, every day it's going to be different. So it'll be different every day. Okay, so it's going to be different every day. And to get credit, you'll need to put this in before a lap over of the class periods. So here, let's. I'll show you the back end of this, and I'll just put in. So let's say this is going to be your password, or hey, everybody always use the John Doe. So here, John Doe, word of the day, apple. You hit a submit. So what happens? Sometimes this comes up, sometimes it does not. So, and this one is looking for all the things that have a traffic light in. Taxis. I don't know that there's a taxi there. Okay, so what happened on my end? Let's take a look. Okay, I'm going to show you what I see. This is not crucial to the lecture, but I'll show you what I see and where things go. Okay. I need to switch into this account. And we are not in here. We are in Dynamics. There is the form. What you see is the numbers are picking up as we go. So here's 8 responses. If you don't mind, I'll go ahead and put this in here. You can see everybody's response, and you can see my goofy one in there somewhere. I don't even know what I did. Oh, Joe Doe. So here is one of the ones I did. Now, what will happen eventually is okay, this is not crucial to the lecture, but the way these things are collected, I create a spreadsheet, it'll dump it over here. And then I will go and read, what you'll notice is the time. So you can see, okay, you can see people filling it out as time goes by. Now, I'm sorry, but it doesn't matter whether it's uppercase or lowercase. That doesn't matter. So as time goes by, it's going to fill out these, and what will happen is I have a timestamp. So it just fills them out as we go through. Eventually what happens is, well, today's Friday, but say this is Monday, and Monday rolls around, and then all of a sudden what happens is on Wednesday we have a new word of the day. Well, at that point, I don't know that there's a way for me to give credit sweeping the files, because you could have two entries on a Wednesday afternoon where one is Monday's word of the day and then the next one is Wednesday's word of the day. So I think the way I'm going to do this is, if you watch it and you keep up and you're at least close enough to it, I can give you extra credits there. So what I'll do, I haven't written the code, but I will write the code later, and you can see right now we've got 11. So as we do this, believe it or not, you can turn around. Let's see. Next time I come in, Dynamics, roll down here in a second, and what you see is it shows up again. So each time you enter it, it doesn't really matter. You could have just refreshed the screen, although I think Blackboard knocks you out. So the form is still there. You just keep using the form over and over and over. So with that in mind, okay, let me head off and do what I was going to do today. And I'm going to look, okay, units, that's kind of self-contained. So what I'm going to do is look at this one. Okay, now what you see is I see things a little bit different. This is what you see. Wait a minute. It popped me back to the main. And now I got to go back in here. So this is what I see. Oh, okay. You do have the things on the left. I thought you didn't get the table of contents. But apparently you get the table of contents. What you don't get is you don't get the ability to scroll down. So you have to go through the pages this way, or you have to select them on the table of contents. So let's take a look at this. I think it might be best if I just, well, I'd tell you what, I can just do this and grab it that way. Oh. Okay, so so here's the particular problem. Okay, so I'm doing this on the screen thing. I'll dump it off in a minute. So position of a particle is along a straight line. Yeah, hang on. Let's bring it down to 1. That's good enough. So here's your position of a particle. And it says t is in seconds. Determine the position of the particle when it's 6 seconds and the total distance it travels. Okay, before you even do anything, it's probably a good idea to do a plot on it. And it looks like he's only interested in 6 seconds. Now, I'm using Octave, and what I did is I kind of reduced it down. So in other words, when you load this up, you get all these workspaces. And I'm going to go ahead and cut them all off except the command window. That way I use the best of my screen. Okay, so looks like I'm having trouble with the command window. So let's see. Let me just restart this thing. It'll show up in a minute. That's really strange. So there's the command window. There must have been something that happened there. Because now I have my two values there. So the way you can do things, let's see. He's obviously starting at 0. Just so that I can get enough resolution, I'll do 0.1, and I'll go ahead and do this to 6 seconds. Now, usually you'd put the semicolon to stop the output, but I'm going to go ahead and do that to show you the output. So here's the output. It just produces a vector. You can see here's the vector. I don't have enough. So my vector is 61 long, and it just contains a bunch of values that are strung from 0 to 6 seconds. And now I'm going to put in S. S is equal to 1.5 times T, and I have to admit I cannot read that now. Okay. Oh, it's T to the third. Okay. So T. Now, if it's a vector, you can do this. Let's try this. If I just do that, you'll see it'll give you an error. But if you put a period, it's what's called an element by element multiplication, or in this case, a power. Minus 13.5 times T squared plus 22.5 times T. I don't have to put a thing there. Now, this time the values are listed here. The dimensions are here. Same dimensions, but now I'm going to plot. I don't know which one to plot, whether I want to plot S versus T or T versus S. Usually, actually, I should have done that in the reverse. Okay, let me do that in the reverse. Because T usually goes along the X where the X goes. Okay, so here is the path of this particle. So essentially, almost looks kind of like a funny sine wave. So what I'm going to do is I'm going to do a small capture of this thing and drop it on. Oh, I can't do that here. I'll drop it over here on this. What do we got going here? Looks like, oh, I've got something there. So let's add a page. Drop out of here. Let's drop this here. So, okay, see if I can remember. S. That's a little too big. Okay, so in any case, I can't. Here, I'll tell you what. Let's see if I can grab it. Oh, I think I did away with it. So I'll need to go back here. Here. I'll grab it here. Okay, this way I don't have to think about it. Okay, so I actually had this equation plotted right here. So what happens is the particle starts here, and this is time, and this was S. So the particle takes off and goes up to here. Then it sort of slows down and stops, and we'll play around with this thing for a second. Then it heads the other direction, goes all the way down to here, then it stops and heads back this way. Now again, you have to remember, here's my S. There really isn't a time. I probably should have done it the other way, but I already did it this way. So in other words, it starts here, moves all the way out to what looks like 10, moves all the way back up, back the other direction to minus whatever. Looks like 40 or something. So the total distance it's traveled is quite a distance here. But it wants to know the position of the particle when it's 6 seconds. Well, that's easy enough. You just put in 1.5, 6 to the third minus 13.5, 6 squared plus 22.56. That gives you your position at it's 6 seconds. That doesn't tell you how far you traveled. So that's why I plotted this thing. It gives me some idea. Now, in the book, he may sit there and say, well, where is the zero velocities? And it's true, you could probably go through that and find those. But you could also plot the thing. And if I'm not mistaken, I believe, yes, you can zoom in on this the same way you can on the MATLAB. So it looks like it goes further than 10. Looks like it goes 10 and a half in 1 second. And then that's a little different than MATLAB. Then it looks like about 5 seconds. Uh-oh. I think I lost it. Here. Yeah, it looks like about 5 seconds. It heads along and heads back to minus 37.5. You could answer the question by picking the values off the chart and picking the values off this plot, adding up this distance, and this last distance, distance 3. So essentially the distance it traveled was those 3 put together. So that's kind of how you do that. And there's only one other problem here, and it's a particle travels in a straight line with the velocity of that value with that function. When t is equal to 1 second, the particle is located at 10 meters to the left of the origin. Determine the acceleration when t is equal to 4 seconds there. And there's a big gap between those. The displacement from t is equal to 0 to t is equal to 10. Okay, and the distance that traveled. Same thing. Oh, and by the way, I'll show you this after I snip this. If you go to the bottom, now I tried to remember to do this, but getting the right answer, you may think that that's your credit. Your credit is actually coming from working the problem. So these are instructional in the sense that you've got the values at the bottom. So if you don't get them exactly right, I'm not going to mark off. So this is actually for you. It's not necessarily for anything else. So if you look at this, same concept. The difference is, if I can move it back, is this, okay? I now need to, okay, is that you have a velocity equals to 12 minus 3t squared. Wow, there's parentheses, I don't know. But he says when t is equal to 1 second, the particle is located there. Well, at 1 second, it's equal to 10. But I currently don't know s as a function of time. But I have this, and I have this relationship. So I can actually take this, if I can get my fingers here, take this, well, take that, move it to that side, knock this out, do an integral, and I can integrate from 0. Okay, this is, let me take this and move it underneath here. I've sort of, here, I'll take this, here. Oh, that is a finger lasso. Let's try this one. I have to hold the pen thing down, and sometimes that's not that easy to do. And I'm still over here in the lasso, so I'll move this to the right, and I'll actually zoom in on it so that I can focus on it a little bit. So here's the deal, and Here, let's just redo this. Integral of dv equals to integral of s dt. If we start with 0, this is the velocity at 0. We go to t, and this is the velocity at t. So on the left you get v, which you could say this, minus v0. However, often what they do is put this as a subscript, and often they just leave this t off of here, equals to the s, which, well, wait a minute. Okay, so I goofed here. I'm trying to get s. Jeez. Okay. I don't even know what I wrote, so forget everything I wrote there, and let's look at this from this. I don't know what happened there. I didn't have caffeine. So, now, good grief. Okay, now, jeez. And this will just be whatever time that is. And usually this is over on this side, so that may have been what confused me. But I have been staying off caffeine for the last several days. So now, forget that section of the lecture, and we'll have s of t minus s of 0. This is where have that, and often they don't even put this in there. And now, okay, now you can inject this in here. And one of the problems, I mean, I'll go ahead and do this part, but, well, I'll let you do this part, but here's the deal. I get s is equal to whatever s0 is, because I moved it over, plus, I guess I can do this. I got 12t minus 3t to, oh, that's interesting, over to the third. And so the problem is he tells you this. So what you do, okay, so technically I erased it, but that was the case, and you just put in 1 second. Was it 1 equals to 10, which is equal to s naught plus 12 times 1 minus 3 over 1 to the third over 3, and I probably should have canceled that out. And you solve for s naught. That's how you kind of take that place. The next thing you do is, once you have that s naught, is you can do the same thing with that s, and that is, again, depends on the way you want to do it. You could plot s here and t here. I did that first, or you could plot s here and t here. It's obviously going to start whatever this s naught is. It might start somewhere here or negative. I don't know. It might head like this. It's not, okay, it's cubic, so it can only pass the axis like 3 times. So it's going to go up, it's going to turn around and go backwards, and it's going to turn and go wherever. So the same thing happens back here for the distance. Again, the displacement, okay, he says displacement from 0 to 10 seconds. So that would be, okay, this is something you've got to consider too. The displacement is, let's say, for example, it started at 5. So in other words, let's say S0 was equal to 5. And then it ended up over at, well, let's not put it there. Let's put it at 12. Even if it did something bizarre then the displacement would be the 5 minus the 12. So that's the displacement. And again, I think, yeah, I think those are all at the bottom of the page. So those are the only two there. Let's go ahead and look at the next one, which is not homework 2, which is homework 3, because then I can speed through the lectures next time. Let's see. Uh-oh. I do not know what I did there. It's possible my finger hit something. Good grief. Okay. Let's go on to week 3. And there's 3 videos, but I'm going to go straight to the homework. Okay, so this is that erratic motion stuff. So in this, all you're doing is you're recognizing that, and I wonder if I could, let's see, it's possible for me to do this. And here, I'll just do this. And then I'll drop it. Let's see, desktop. Yeah, I'll just do it right there. And now, if I do that, oh, it opens it back in there? It should not do that. I do not know what's going on here. Open with. Okay, finally. Okay, so in this, it's a situation where you have acceleration, give me the pen, acceleration, and time. And remember, we have S, velocity, and acceleration. To go this direction, you basically, I mean, if you think about it, ds dt is equal to velocity. Therefore, if I have S to go this direction, I take a differential. If I'm going this direction, and so here, slope. If I'm going this direction, I obviously do the reverse, which is take an integral or find the area. Okay, so this is a constant. Everything is a constant. It's either 6 or minus 4. Jet car traveled original velocity at this. When it's subject to the acceleration shown, that, determine the car's maximum velocity and the time it takes to stop. You got a little extra problem here, and that is you're starting at 10 meters per second. So if you look at acceleration and you're having to do the integral, or here, this, and let's see. If you're having to do that, then you basically are starting at 0, and the car initially is traveling at 10 because the velocity at 0 is equal to 10. So this has to sit in there. Oops. I don't know what to do with that. So you're going to a certain time, and you're going to the velocity at that time. Now, this is pretty simple because what I can do is on the left-hand side, I can just look at this and say, well, this is just the velocity minus 10. That's what the integral ends up. So to me, I can put in the value of 6 and integrate it, or I can just say, okay, here's my area. Was that 15 times 6? That's the area there. This is, here's what I'll do. I'll just say delta t. This is minus 4 times delta t. Now, he wants to know, determine the car's maximum velocity. So to me, when this thing starts, if you wanted to list it out here, velocity and time, it's going to start at 10, and this is flat, so this has got to be linear. And since it's pushing in a positive direction, as you move and take slices this way, in other words, if you're sitting here looking at this area, this area would basically put you here. In other words, you're moving to the right, you're gaining area. So it's going to be a straight line till you get to right here. Then he pretty much, instead of a constant acceleration, he's putting on the brakes in such a way that it's a constant deceleration. Now, what happens is, if you come in here and look at this plot, the slope of this plot has to be 6. So if you, I did a pretty poor job of, here, let me get rid of this. So here's your line to here. The slope has to be the rise over the run. It's not to scale, by the way. Runs to 6. And this runs to 15 seconds. Then he put on his brakes, and he wants to know how far he goes until he goes here. Now, the first problem is I've got a greater slope here than I do here on the drawing. This slope has to be minus 4 because I'm decelerating. So this is definitely not to scale. The thing would probably look more like this. The slope really tall, and then the slope would come down like this. But I've got it in reverse. But it really doesn't matter. So you can find your maximum velocity here, and you can determine, see, the problem is if you just take this area and subtract it from this area, that gets you back to this 10. So you have to take that extra and push it to the right to the point where you get yourself back to velocities equal to 0. I don't think he asked anything. Oh, and the time at delta, this t prime, when it stops. When t is equal to 0, s is equal to 0. I don't know what he had. Vmax of 100 and in 40 seconds. I don't know. If you look at 10 plus what? 6 times 15. See, 6 times that 60, and then 30. 60, and then 30, and then 10. This will go that, make 70. That'll go that, make 100. So essentially, that's correct. In other words, what I'm saying is, if you have a slope of 6 and you want to know the distance that you moved in 15, you multiply 6 times 15, gives you this delta. Add that to 10, and that gives you 100. So I'll let you work with that one. Let's go to the next one. The race car starts at rest. Okay, so starts at rest, SC was equal to 0, and travels in a straight road until it reaches a speed of 26 at Okay, 26 at 8 seconds, as shown on the velocity time diagram. The flat portion is caused by shifting gears. When draw the AT graph and determine the maximum acceleration. That's pretty easy. Slope, 3.5. Slope, nothing. And then slope, 4. So that's 3.5. This is 4. So there you go. Determine the maximum acceleration of the car. That's just 4. Why is there a big asterisk up there? Okay, where is the problem? Okay, I have no idea what that is. That may be a page that is supposed to be later. Okay, so if I go down, yeah, I bet you that page, this page is supposed to be under that page. So sorry about that. And I'm not even sure of that. So this page may be the answer to this problem, because if I go to the bottom here, I don't see an answer there. So the motion of the jet, okay, so there's your acceleration, there's your T. So obviously, again, S to V to acceleration. If you're going this way, you're differentiating. If you're going this way, you're integrating, which means you have a constant of integration, which probably is the annoyance that you see there. I don't know. Okay, so the jet airplane, just after landing on the runway, is described by that. Determine the time when the plane stops. Okay, construct the diagrams here. S0 is equal to 0, and V is equal to 300 feet. So V0 would be 300. So essentially, I'm going to do a half-hearted attempt here. So here's your 300. Okay, I'm taking it maybe incorrectly, but I see this blue line. I look at it like it's going here, then here, then here, and then this way, and then that. So if it's coming in for the first 10 seconds, nothing's happening. Then, as the area increases, okay, so now from 10 to 20, I have a linear. So again, let's take this off. Let's look over here. Okay, so if this is constant, then this is first order, and this is second order. This is between 10 and 20. Okay, so I'll make a little table here. Between 10 and 20, and I can erase it in a minute. It's linear, or first order, so this is second order, and this is third order. Okay, from 20 to the end, it's constant, or 0th order, then first order, and then second order. So the first section, I'm going to have to pay attention to and say, hey, you know, this is not constant anymore. So I will have to come up with what this is. So for lack of a better word, I'll say it looks linear. So I'm going to say the acceleration is equal to just some constant 1 times time plus some constant 2. Now, if I want to know what the constants are, I look at the line there. First of all, what's the slope? Okay, so if I go, the rise is 10, the run is 10. So it looks like it's 1 times t, or I can just list this as t. Acceleration is equal to t plus whatever the second constant is. So it is true, that's an intercept, and you can go down and try to find it, or you can do this. You can say to yourself, well, my acceleration at t is equal to 10 seconds has to match this. T, that's 10 seconds, Oh, wait, I got to put down that. It's minus 20. Minus 20 is equal to 10 t, put in t here, plus c2, and there's for c2's got to be moved that over, and you get minus 30. So from a little bit of poking around at this thing, found that the acceleration is equal to t minus 30 for that short period of time. Let's see if this is the actual answer. I can't make heads or tails. Well, he doesn't have acceleration listed here. So now let's go ahead and we're sticking between 10 and 20 for a while. So we're sticking in this region right here. So let's take a look at this. My acceleration. Okay, so if I want to look at it, I'll look up here. dv dt equals to acceleration. So if I want to basically pull that across, integral and integral of dv. Now here, and this can only happen between 10 and 20. So, and I'm running out of space, t minus 30 dt. Now, where do I want to go to and from? And so obviously, the first thing I can say is it can't happen before 10. So I'm going to put down 10 seconds. And I'm going to say the velocity at 10 seconds. Well, what is the velocity at 10 seconds? Well, no acceleration happened. So I'm still at the 300. So I could put in the 300. And then I could say velocity and time. As long as this time is less than 20, this is all valid. So here, I'm going to go ahead and try something interesting and see if this works. I do not know if this will allow me to do this. I did. So now, and only that, I will shrink it down. The beauty of digital culture is that you can change your size and fit anything on the page. So if I integrate this, I get velocity at some time minus 300 is equal to, now I take this and I get t squared over 2 minus 30t from 0 to t. And that was as long as that's the case. So if I want to list this as velocity as a function of time, I can move my 30 over. Plus, okay, now I made a big mistake there because that should have been 10. Now, t squared, I'm just putting the top thing in, 30t minus, okay, because I'm taking the 10 in here, and I'll put this, we'll go ahead and square it over 2 minus 30 times 10. That'll give me 50. Ooh, this will give me minus 300. So that'll give me minus 250. So let's see. My velocity as a function of time, take that 250 and knock 30 off of it, and I believe I'm going to list the t squareds first. Okay, minus 30 t minus, with this 250 knocking 30, I get 220. Question number 1 that you should ask when you have something like this. Does the velocity at t equal to 10 equal to, and this is a question mark, it's supposed to be equal to 300 because that was what we started with. So let's check it. So we've got 10. I'm basically going to take this part of the equation and redo it down here. So I got 10 squared 100 minus 30 times 10 minus 220. That's 50 minus 300 minus 220. Already I see a problem. I have forgot a sign, or I've done something, because it is not going to be 300. So somewhere in here I have shown an error. So there is an error here. I can let you find it, and probably it's coming out of the fact that I got a minus and a minus there. So this probably should be plus, but there I've already goofed up a couple things here. So this is minus signs and things like that. So I'm going to let you fix this, but you get the basic gist of this. The problem is the check tells me that something's wrong. So I would say that's definitely wrong there. Don't know if that's, I can look at the answer just like any normal person would do. If we look here, you see the t squared and the minus 30, t squared and the minus 30, and obviously there was the problem. So I have goofed up here mostly because I have had to, so the minus signs here, I'll let you fix all that, and I'll just go on. So that's the last one there. And so that covers us through the next 2 weeks. Now, if we head back and end up in here, okay, let me see if I can go to, there's a calendar here, course calendar. My calendar will be, have included in it my other courses as well. So today's the 21st. So the first one on units is due this day. Now I don't know, that is this one. So that color is the dynamics. So turn that in by, it says 11. Some of these I may be, oh, okay. I have a funny feeling this had to do with the time change. Okay. Nothing's showing up. That's very strange. Okay. Oh, I know why it's not showing up. Because those weeks are not open. For me, without the student preview, I go to the calendar and they will be opened. So if I go, uh-oh, what is that supposed to do at 8:30? Oh, geez. So I'll have to go take a look at that later. Good grief. Monday through Thursday, I got something I'm supposed to do at 8:30. Okay, so now this is the week that that I haven't turned on yet or made available. And so that takes us all the way through the semester. This is the spring break, and obviously it looks like to me that's the spring break because there's something I have to do that I'm going to have to check. It's probably some sort of weird assignment they've given me. They now use Blackboard. It obviously started on the 19th. I'll deal with that later. I don't know what that is. Oh my gosh, look at all this. Okay, so I guess we're pretty much done. We covered the 2 homeworks. We're going to try to make it to class on Monday. I'll send you an email. But on the other hand, if you are ill or you don't want to attend, it's going to be live streamed anyway. I'll set up the live stream things the way I've done, and I'll just send that to you. There is one thing that I will tell you, and I'm going to add to this. I don't know. Let's see if I can do this. I guess I could tell you later. If you go in, wait patiently. Yeah, let's just do that. YouTube. I'm sorry I'm going over here. I wouldn't go over if the thing was... Okay, so if I go here, okay, then I go in here. That was the one that's left. So you can go to videos, okay, and it should list. So this is the one that's going on now, but you can have this button. There's a live now because there is one live now. So if you go to videos, all videos upload live now. If you go to live now, that's the one we're on. If you go to upcoming live streams, you'll see these. And then past live streams, you'll see those. The first week was pretty much a crazy washout. So we're getting up steam and we're going with this now. So with that, I'm done. I need to drop out, get on to the next class here.